Now, let's talk about that tutorial this week. You found that in your car there are three ways to accelerate, three accelerators. If you have an acceleration vector in the same direction as your velocity vector, you are using your gas pedal. You are speeding up on a straight road. You are not using your steering wheel, just your gas pedal. Now, the change in velocity that happens every interval of time has to be in the same direction as that acceleration. So I'm adding a change in velocity in the same direction, making the velocity vector longer and longer. If I have an acceleration vector in the opposite direction, well, now I'm using my brake. And the acceleration gives me the direction of the change in velocity. Opposite the velocity makes the velocity vector shorter and shorter. Now, if that acceleration is not in the same direction as velocity and not in the opposite direction, the only thing left is perpendicular. And in that case, you're using your steering wheel. You're changing direction. You're doing it with cruise control on because you're not changing your speed. You're adding a little change in velocity, perpendicular, that changes the direction of your vector. Now suppose I have a truck going around an elliptical track at constant speed. And you notice that I emphasize that word speed. It can't be velocity. I can't go around that track with constant velocity. Why not? Velocity has direction. You can't go around a corner with constant velocity. Now, if I were to ask you where the acceleration would have the greatest magnitude, you'd know the answer. You felt it. It's here. Acceleration is something you feel. That's why you pay money at Disney World, to feel acceleration. When you speed up, you fly backwards. When you slow down, you fly forwards. When you turn right, you fly to the left. That's exciting. That's what you pay your money for. Now, if you're going around this track at 60 miles an hour, you know you feel it more here than you do there. Now, we can show that with vectors. If I look at the velocity vector there, and I want to know what does the acceleration look like? Well, the acceleration is how much that velocity vector changes in 1 second. So let's look a half second before and a half second after. If that's a half second before and that's a half second after, that's 1 second. Okay? Well, those two vectors have the same length, same speed, but they're not the same velocity. And I can see how different they are by putting them tail to tail and finding the change vector. The change vector is what I have to add, there's a plus sign right there, to the earlier velocity to get the later velocity. Now, because that change happened in a second, that is the acceleration. Now, if I did that same thing at this other part of the track where it's more severe, again, I go a half second before, a half second after. These vectors are the same length as each other. Indeed, they're the same length as the earlier vectors. But now you can see that those vectors are drastically different. They're different in direction. When I look at how different they are, I put them tail to tail. I find the change vector that I have to add to the initial to get the final. That change happens in a second, so that's my acceleration. I get a big acceleration here where the curvature is tight, a small acceleration here where it's gentle. Okay, that's just a quick review of what you learned in this week's tutorial. Now, what if you speed up as you go around this track? Well, your velocity vectors would get longer and longer. Now, if I asked you for the acceleration here, with your finger, just point in the direction of the acceleration. Everyone, come on, you can do it. Okay? Everyone, I think pretty much everyone's pointing the right direction. It's like that. Now, folks, I want you to see that as a combination of two flavors. There's three flavors of acceleration: speeding up, slowing down, turning. And just like ice cream, you can mix it. In this case, I'm turning left, and that takes an acceleration which is 90 degrees to the velocity. I'm also speeding up. That gives me an acceleration that's in the same direction as the velocity. Okay? When I add those two components, the gas pedal, and the steering wheel, I get this vector that's less than 90 degrees. Okay? Now, what you should have learned, what the takeaway was from that tutorial is, if I've got a car, those are the wheels, I can't draw. The velocity vector always goes out the front windshield if you're going forward. Now, if I want to turn right, I have to have an acceleration like this. If I want to go straight but speed up, or slow down, let's do slow down. That would be an acceleration that would slow me down. But it would not turn me. If I'm turning right and slowing down, I would have to have both flavors. Likewise, if I wanted to turn left, I'd have to have an acceleration like this. And if I wanted to speed up and turn left, I would have to have an acceleration like that. Now, people, you have to be careful with your words. I find that after this tutorial, some people are worse off than they were before. They get broken by the tutorial. Why? Because they're lazy and they just memorize a very simple little formula. They say, oh, if the angle between the acceleration and the velocity is less than 90, that's speeding up. How many of you came away from tutorial with that? That's wrong. Sick and wrong. If the angle between the velocity and the acceleration is less than 90, that's speeding up. Finish the sentence. And turning. And turning. Okay? If the angle between the velocity and the acceleration is greater than 90, that's slowing down. And turning. But if you're on a straight road and you're not using your steering wheel, then by golly, speeding up is 0 degrees. It's not less than 90, it's 0. And slowing down is 180 degrees. Okay? Period. Okay.